Alright, so let's dive into this other topic called implicit differentiation. Implicit. I'm not going to spell out differentiation, but that's the topic. So what is implicit differentiation? Implicit differentiation is basically taking an equation, and the equation is going to have two variables in it. Today we're just going to see equations with variables called x and y, just to make it simple, but again, you can call the variables anything you want, as long as they are separate. So you're going to take an equation with two variables, and you're going to find an equation for the slope at any point. So similar to a derivative, but you're going to be taking the derivative of each variable as if that variable is a function of the other. So for example, if an equation has an x in it, and you take the derivative with respect to that, then you'll just get 1. If it has a y in it, and you take the derivative with respect to it, and this time it's with respect to x of y, it's going to be something different. So we don't actually know what y is. Y could be, it could just be a constant. It could be, x squared minus 3. It could be some crazy like logarithm of sine of x. It could be anything. We don't know what that is at the moment. So when we take the derivative with respect to x, we simply get this, dy over dx. We could also call that y prime, or dy. Again, that's all we're saying. We take the derivative of that. So where this really comes into play is when you have parts of an equation that might have, x times y. In this case, if we take the derivative of that entire thing, of x times y, you have to use the product rule, because y in this case is not just a constant. It's not just a 3 that you could take out. It's not a pi or anything. So you have to take the derivative of both the first and the second parts. So for this small example, if we took the derivative of this, you would get the first times the derivative of the second. So what we said the derivative of y with respect to x is dy over dx, plus the second y times the derivative of the first. I know this is going to look confusing at first, but the more practice you have with it, the easier it becomes, and eventually becomes really second nature, especially if you continue on to learn more about differential equations. If you go into physics, it's huge in physics, specifically astrophysics. I'm an unbiased source as I am currently studying astrophysics, but yeah, you'll see this a lot if you get into those higher level mathematics courses and subjects. That's just one example. Let me start off with a simple problem where we apply this this concept of implicit differentiation. So, what if we have this equation? 5x squared plus, minus, we're going to do minus y cubed equals 7. Now these problems are going to be worded in that they want you to find something like dy over dx. So they'll say find dy over dx, or find y prime. So that's what it's going to want you to find. At first, this could look a little challenging, but all you're doing is just taking the derivative of each side of the equation. So let's work through this one. So we want to find dy over dx, and the first step is to just take the derivative of each side. So the left-hand side, we are going to be finding the derivative of 5x squared minus y cubed And then on the right hand side, same thing, but we're just finding the derivative of 7. Immediately from our derivative rules, we know that the derivative of a constant is just 0. So the right hand side is very easy. The left hand side, we're going to have to split it up a little bit. So again, with derivative rules, the derivative of 5x squared minus y cubed is 5x squared minus the derivative of y cubed, because you can really just pass this derivative operator really into each piece to separate it out, make it a little easier. That is still going to be equal to 0. Alright, so let's start with the first piece on the left hand side. So it's a simple derivative, the derivative of 5x squared. We bring the 2 down, we get 10x, and then we subtract 1 from the exponent, so we get 10x. And we're going to subtract y cubed. So how are we going to do this one? So we want to take the derivative with respect to x of y that we know is a function of x cubed. So we could do u substitution and say that u equals y of x, and we're just taking the derivative with respect to u. So I'm not actually going to write out the u substitution, but really when you see this, just treat the y as its own variable and still follow the same rules as if it's x, knowing that at the end you're going to have to add the extra piece, the u prime. So we have the derivative of y cubed, which is going to be 3y squared. But then we don't know what y is at the moment, so we're going to end up with dy, which in this case I'm going to call it dy over dx. Because we just know we're trying to find the derivative of y is kind of what we're saying it is. Alright, so that's what we get on the left hand side, and it's still equal to 0. So if we go back to the top, if this loads, it looks like it's not going to load for some reason, but we were asked to find dy over dx. So find dy over dx is the goal. And we really have an equation with dy dx in it, so all we have to do now, step 2, is just solve for dy dx. So we can move the 10x to the other side. We get negative 3y squared. Dy over dx equals negative 10x. We can multiply both sides by negative 1 just to get that negative to go away. And then we can divide by 3y squared. And we are left with dy over dx equals 10x over 3y squared. And there we go. Alright, let's do another example. So now we're going to try one that's a little bit larger. So x squared minus 4xy plus y squared equals 4. Alright, so same thing. We want to find dy over dx. So find dy over dx. So step 1, just take the derivative of each side. So we're going to take the derivative of this whole thing. I'm actually going to just write each piece out ahead of time so I'm not copying the same equation over and over again. So this is going to be the derivative with respect to x of x squared minus the derivative of 4xy plus the derivative of y squared equals the derivative of 4. So same as the problem above, the right hand side is just 0 because the derivative of a constant is 0. Alright, so let's start with this piece on the left hand side. The derivative of x squared is 2x. Now we're going to subtract And also the reason why x squared, after you take the derivative, we don't do the dx is just because dx is 1. So when we take the derivative with something with y in it, we have to have the dy over dx. So that's just one thing. There is actually dx here, but I'm not actually going to be writing that out each time. Only when there's a y in the equation. Alright, so we have 2x, and we are subtracting the derivative of 4 times, and I just pulled the 4 out to the front since it's a constant. And now we have two variables in here. We have x and y is a function of x. So we have to use the product rule again. So here we have the derivative of x times y is the first, so x, times the derivative of the second, so y. The derivative of the second is 1 times dy dx. Y dy dx, because y is a function of x, plus the second times the derivative of the first. Alright. And then now we find the derivative of y squared. So that is 2y. We bring the 2 down, subtract 1 from the exponent. And then since it's a y, we have to multiply it by dy over dx. And that whole thing is equal to 0. Alright, so there's a few more terms in this that we ended up with than last time. But we can still solve for dy over dx, even though there's really two places that it shows up. So the first thing I'm going to do is kind of distribute everything out so that each part of this is kind of as spread out as possible, so we can just take the pieces we want with dy dx in them and move them over to the right. So this becomes 2x minus 4x dy dx plus minus, because we're distributing the negative 4, minus 4y plus 2y dy dx equals 0. So from both sides of the equation, I'm going to I'm going to add 4x dy over dx and subtract 2y dy over dx, so that we remove it from the left-hand side and move it over to the right-hand side. So I'm going to add that and subtract that. And on the left-hand side, we are left with 2x minus 4y, because we're left with these. On the right-hand side, we end up with 4x dy over dx minus 2y dy over dx. And now each of these terms on the right-hand side both have a dy over dx, so we can pull that out. We get the same thing on the left-hand side, and we are left with 4x minus 2y, all multiplied by dy over dx. And now we can divide each side by what's in these parentheses. So 4x minus 2y, 4x minus 2y, and we are left with dy dx by itself on the right-hand side. On the left-hand side, we have 2x minus 4y minus 4x minus 2y, divided by 4x minus 2y. Each of these terms has a 2, so I can really cancel the 2's here. Cancel the 2's. And we are left with x minus 2y all over 2x minus y. And sometimes I've seen, it's personal preference, but sometimes I've seen people that like to put the y's in the front. So you can kind of multiply both the top and the bottom by -1, and it's equal to the same thing, but you can kind of flip the order to 2y minus x over y minus 2x. That equals dy over dx. Make sure I didn't screw something up. Yeah. Alright. Let's do a couple more problems. Alright, let's try a slightly harder one now. I'm just going to change the ink color. I'm getting kind of tired of the black ink. Let's see. Let me make the size of it a little bit larger. There we go. Okay. So, let's say same type of question, but this time the equation is x squared over x plus y equals y squared plus 1. Again, we want to find dy dx. So, same steps as above. This is just going to be a little bit messier of a problem because this equation is a good bit more complex than the last ones we used. But it's still going to be the same steps. So we want the derivative of the left-hand side. Let's set that equal to the derivative of the right-hand side. Also, as a side point, we are always doing the derivative with respect to x because it's asking us for dy over dx. If it asked us for dx over dy, we would do the same steps, but we would differentiate with respect to y. Alright, so let's start with the left-hand side. So before we were always using the product rule because that's just how the problem was set up. Now we have to branch out a little more and use the quotient rule. So if we remember the quotient rule from before, the derivative of a quotient is the bottom, so x plus y, times the derivative of the top. So in this case, derivative of the top, x squared, I bring the 2 down, we'll just get 2x. Minus, this time, the top, x squared, times the derivative of the bottom, so d over dx of x plus d over dx of y. And really I got this, I moved ahead a little bit faster and just said instead of taking the derivative of the bottom, I already distributed this derivative to each piece. So I have the top here, x squared, times the derivative of the bottom, which is d over dx x, plus d over dx y. All of this is going to be over, or divided by, the bottom squared to finish off the quotient rule. And if you ever forget these rules, you can just look them up in a derivative table. The only reason I remember it is I just use it so often in my studies that it's kind of second nature to me now. But we did the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. On the right-hand side, we have to take that derivative now. So we get the derivative of y squared plus the derivative of 1, which derivative of 1 is a constant, so that becomes 0. So let me rewrite this on the bottom. So x plus y times 2x minus x squared times, and now I'll actually start finishing off these derivatives. So the derivative with respect to x is just 1 plus derivative with respect to y. We actually can't really do anything with it, so it just becomes dy dx. I'm just kind of absorbing this y up with the d. So dy dx divided by x plus y squared equals, now the derivative of y squared, like we said before, 2y, but then we have to include the y prime. So dy over dx. Alright, and now we can try to separate the dy and the dx. So how I'm going to do this, I'm going to first multiply both sides by this bottom piece here, so that we don't have any fractions. So when we do that, we get the top part of this fraction minus, I'm going to actually distribute this x squared as well, minus x squared minus x squared dy dx equals 2y x plus y squared dy dx. Alright, now I'm going to add to each side this term here, because this is the only one on the left hand side that has the dy dx. Rather than write that again, it hasn't changed. That's going to be plus x squared dy dx. Alright, so let me rewrite this now. And as I rewrite it, I'm also going to distribute this. This is kind of how I do it personally, just with each step. I just kind of take it in pieces. If I did every single thing by itself, it might be a lot of lines of math work, but do whatever is most comfortable to you. This is just kind of my habit. As I slowly expand things as I'm moving down and doing the calculation. So we distribute this 2x, we get 2x squared plus 2xy minus x squared. And then since we added this, this goes away on the left hand side. On the right hand side, we have 2y x plus y squared dy dx plus x squared dy dx. And now, since we have dy dx multiplied by each piece, we can take it out and make it by itself, move it to be by itself. On the left hand side, we are left with the same thing, 2x squared plus 2xy minus x squared equals 2y x plus y squared plus x squared times dy over dx. Alright, and then the last step to move dy dx by itself, we just divide this, both sides by this. So we get 2x squared plus 2xy minus x squared divided by 2y times x plus y squared plus x squared. And that equals dy dx. Alright, we can clean this side up here a little bit though. There's still, things in brackets that are squared. This negative x squared can be taken away from this 2x squared. So let me clean this up a little bit. So on the top, negative x squared, 2x squared, that 2 can go away. So on the top, we're just left with x squared plus 2xy. On the bottom, I'm also going to expand this out and multiply it out with the 2y. So we get 2y times, we're going to FOIL the x plus y squared, so we get x squared plus 2xy plus y squared, all of that multiplied by 2y and then added to x squared. So I'm going to multiply the 2y out, and we get x squared plus 2xy on the top divided by 2yx squared plus 4xy squared plus 2y cubed plus x squared. And that's going to equal dy over dx. And that's your answer. And really the final way you present this is kind of personal preference. I just like having it split up to be polynomials on the top and the bottom. But this is equally correct as what we had here before I messed it up with all the markings. They're all equally correct. This is just kind of my opinion of what I think looks the nicest. Alright, so we're going to do a problem that is a little bit more involved now. This one has some trigonometry some trigonometric functions that we're going to have to be differentiating. So here's the equation. Sine of x plus y equals cosine x plus cosine y. And again, we're going to be finding dy dx. So same as before, we need to do the two steps. First step is to take the derivative of the left-hand side and the right-hand side. So the derivative of sine of x plus y, that's going to equal the derivative of cosine of x plus the derivative of cosine of y. So I'm going to start with the left-hand side here first. So this derivative is actually very difficult to take as it is. Really, we don't. If you look through the derivative rule table that you can find if you Google, or likely if you're in a class, it's not going to be on there. You're not going to find a derivative rule for a sine of two variables added together. So to take this derivative, we have to turn this sine of x plus y into something that we can take the derivative of. So I actually ended up looking in a table of trigonometry rules to see how we can rewrite sine of x plus y into something that we can take the derivative of. And I did find we can rewrite this as sine of x plus y, again this is from a trigonometry table, is equal to sine x times cosine y plus cosine x times sine of y. And now, even though this is a lot more terms, this is just a summation of two smaller functions multiplied together. And each of these multiplications, each piece of this is something that you can take the derivative of because it's on any old derivative table. So this is going to be a little bit lengthy, but let's go ahead and do it. So we're going to distribute this derivative to each summation. So we're first going to focus on this guy. So sine x times cosine of y. So we have to use the product rule here. The product rule says that this derivative is the first, so sine of x, times the derivative of the second. So derivative of cosine of y is negative sine of y. And since it's a function of y, we have to add the dy dx at the end. Plus the second, so cosine of y, times the derivative of the first, which is just cosine of x. So that is that part. So now we're going to do this part, cosine of x sine y. So it's the exact same type of thing, the product rule. So we're going to start with cosine of x times the derivative of the second, so derivative of sine of y is cosine of y dy dx, plus the second, so sine of y, times the derivative of the first, so negative sine of x. And that is this large derivative. That is the left-hand side. Now we can move on to the right-hand side. I'm going to switch my color back to blue. So now we can focus on this here. This is a lot easier to do because it's just two individual pieces. So all of this down here below is going to equal the derivative of cosine of x, which is negative sine of x, plus the derivative of cosine of y, which is negative sine of y dy dx. Alright, so this is our massive function now. This is the right-hand side. So the second step is to separate out all the pieces with dy dx, move them all onto the same side, take out the dy dx and solve for it. Alright, so I'm going to move all of these pieces, the dy dx, onto the right hand side. So this giant equation here is going to equal, I'm going to start with this because it's already on the right hand side, so negative sine of y dy dx. Alright, and then I'm going to move this to the other side, which means it becomes negative. So it's going to be minus cosine of x cosine of y dy dx. And then this, it already has a negative, so this is going to be positive. So we have plus sine x sine y dy dx. Alright, so we're done with that one, and that one. And what's left, we put on the left-hand side. So what's already on the left-hand side is this cosine y cosine x, cosine y cosine x, and this negative sine y sine x, and we got to move this to the other side. So this negative is going to become a positive, and we're going to have sine of x. And that is all the pieces. So moving on down, on the right hand side, we can pull out the dy dx because it is inside each term here. So this is going to equal dy dx times this whole thing. So negative sine of y minus cosine x cosine y plus sine x sine y. On the left hand side, we have the exact same thing. I'm actually going to rewrite this so that the x's are before the y's. Cosine x cosine y minus sine x sine y plus sine x. That's just personal preference. Now we're going to divide the right hand side by this giant monstrosity here to create a new monstrosity, but we will have dy dx by itself. Alright, so on the left hand side we now have cosine x cosine y minus sine x sine y plus sine of x. That's going to be divided by this whole thing. So minus sine y minus cosine x cosine y plus sine x sine y. Alright, so we have done the second step, and this is technically correct, but like I said before, this is kind of a monstrosity. It is equal to dy dx, but we can do some things to clean this up. So like we did in the beginning, we had a trigonometry rule that converted what was it, sine of x plus y into two pieces that had multiplications. So, an addition of two trigonometry terms that were multiplied together. What we can do is we can actually turn this back into something more condensed, like what we started from. Because we do have the same thing. We have cosine x times cosine y, so two trigonometric functions multiplied together, subtracted by two more multiplied together. This looks very similar. It's not exactly the same because there's a negative, but it looks very similar to what we started with. So checking a trigonometry table, I actually did this ahead of time, but it didn't take too much time to just take a quick check, and I found something that the solution looks a lot like this. So going backwards, we can turn this cosine x cosine y minus sine x sine y into cosine of x plus y. So this here is equal to cosine of x plus y, and then we still have this plus sine of x. And similarly on the bottom, we can turn this into something as well. Unfortunately, it's similar, but it's not quite the same as what we did up here. So what I actually ended up doing was I put a negative in front of this, and then put a negative to every term in the denominator. So overall, this is basically the same thing as saying we're going to multiply -1 over -1 to the top and the bottom, so that it's still the same, it's still equal to the same thing. But we really, essentially, we're taking this negative out, and we're going to rewrite this as sine of y plus cosine of x, cosine of y minus sine of x, sine of y. So that's just from taking this negative out, moving it to the outside. And then we have the same thing that we had above. So this now becomes cosine of x plus y plus sine of x over, and again this is now also cosine of x plus y. So we have another cosine of x plus y on the bottom now, plus sine of y. And that is a much nicer looking and more condensed, more concise answer for dy dx. Alright, let's move on to one last problem. The last problem, we're going to choose this equation. So y times e raised to the power of sine x equals x cosine of y. We want to find dy dx, but this time we also want to find an equation with an equation for the slope with x and y equals 0 and 0. So there's one other step. We're actually going to be solving this final equation to find an equation for dy dx. In other words, we're finding the equation for the line tangent to the curve at 0, 0. Just as a reminder, if we have some curve, we find the slope of that line by taking the derivative. That line can have an equation. That line has an equation defining it, and this is going to help us find the equation of that line if this was the point 0, 0 for some reason. But I know this isn't going through the origin, but if the axes were set up like that and that was the line, we're finding the equation for the tangent line at that point 0, 0. Alright, let me make room for this. And this last step is not very hard. Alright, this equation though is going to be a little bit difficult. So we're going to start out like we always do. Actually, this one, instead of doing dy dx, let's do dx dy. So this time we're going to start, but take the derivative with respect to y. And I'm doing this because the problems aren't always going to have you do dy dx. And it can go both ways. You can take the derivative with respect to either variable and still end up finding an equation for the slope, but with respect to the other variable. So the derivative with respect to y at the left-hand side is a product, so we're going to have to use the product rule again. And so is the right-hand side, actually. X times cosine of y. Alright, so we're taking the derivative with respect to y. On the left-hand side, we'll do the quotient rule, so we have the first times the derivative of the second. So for now, because we're going to have to do another rule here to solve this, I'm going to write this for now. So we have the first times the derivative of the second plus the second times the derivative of the first. And we are taking the derivative with respect to y. So this time we can just do 1. We don't have to do the dy dx because here the variable is kind of reversed. So this time when we do take the derivative, for example here, this is in terms of x, we're going to have to add dx dy in the end. But we'll do that in a second. Alright, so we have the left-hand side, and this is going to equal this derivative. So let's do another product rule. So take the first times the derivative of the second. So derivative of negative, or cosine of y is negative sine of y, plus the second, so plus cosine of y, times the derivative of the first. So derivative of x is 1, but it's with respect to y. So it's really 1 times dy dx, or sorry, dx dy. So we have dx dy. Alright, so let's keep moving. We can finish taking this derivative. We have to finish taking this derivative before we can start solving for dx dy. Alright, so this is going to equal y times, and now taking the derivative e to the sine x, we would have to do really u substitution with u being sine of x. So I'm gonna do it a little fast. If you want to see more detail of kind of how to do this type of derivative, I have videos that I posted in the past outlining how you do u substitution. But this is going to equal e to the sine x times the derivative of what we had in the top there, so times cosine of x. But since this is taken in with respect to y, we want to include the, oh man, I keep doing that, dx dy. And so that is that derivative. Now we have plus e to the sine of x equals negative x sine y plus cosine of y dx dy. Alright, so let's move the two pieces with dx dy onto the right hand side. So to do that, we're going to keep this on this side, so y e to the sine of x plus e to the sine of x. And now I'm going to move this to the other side by making this positive and moving it over. So plus x sine of y. On the right hand side we'll have cosine of y dx dy, and we're I accidentally kept this here. Okay, yeah, my bad. So this whole thing is multiplied together. So on the left-hand side, we actually don't include this y e to the sine x term. So we just have this e to the sine x and plus x sine y. So we're subtracting this entire term on the left-hand side to move to the right-hand side. So now we have minus y e to the sine x cosine of x dx dy. Alright, so we can pull the dx dy out. Dx dy. We are left with cosine of y minus y e to the sine x cosine x. And we have the same thing on the right hand side. E to the sine x plus x sine y. Now we can divide this, each side by that, to get dx dy by itself. And we are left with e to the sine x plus x sine y, all divided by cosine y minus y e to the sine x cosine x. Alright, so this is kind of a mess. Honestly, I'm not exactly sure how to simplify this further. But to finish the problem, we said we wanted to find an equation when x and y are both equal to 0. And again, that finds that the equation of that tangent, of that line at that point that's tangent to the curve. So when x equals 0 equals y, we just plug these directly into the equation. So e raised to the power of sine of x, with x being 0. Sine of 0 is 0. So this just becomes 1. So on the top we have 1, this piece. X times sine of y is just 0, because x is 0. On the bottom we have cosine of 0, which is 1, minus y times all this stuff. And y is 0, so we know that's going to be 0. So we really get 1 equals, we get 1 here equals dx dy. And that's really your equation. 1 equals dx dy. If we integrate, which I know we haven't really done integration yet, but basically integration is going the opposite way. But if we can split this to be by itself, and we have dy, if we multiply both sides by dy, we get dy equals dx. And if we did integrate, the opposite of the derivative of y is just y. Opposite of the derivative of x is just x. And y equals x is the equation for that tangent line. Alright, that is really the basics of implicit differentiation. I probably won't hit this topic too much anymore, but just know if you do continue in physics or higher level mathematics, this will likely show up a number of times, and it will be integral to carrying out some of those problems and calculations. Alright, that's all I have for this video, and I will see you next time.